Okay, take a quick second and just look around you right now. Your smartphone, your laptop, the TV on your wall, or even just the simple fan spinning overhead. Every single one of them runs on a circuit. And what's truly mind-blowing is that every one of these highly complex circuits is built from the exact same small family of parts.
Welcome to this explainer. Today, we're diving into a foundational overview of electrical components. You can think of these components as the fundamental building blocks of basically all modern technology. I mean, electricity on its own is just raw, unbridled power, right? But when we harness it using these specific, standardized little pieces, it transforms into the incredible technologies that literally run our modern world.
So here's our roadmap for today. We're going to cover the vocabulary of circuits, the difference between passive and active families, and then we'll jump into the big three: the resistor, the capacitor, and finally the inductor.
All right, part 1, the vocabulary of circuits, essentially the basic language of electronics.
You know, raw electricity only becomes actually useful to us when it's shaped, stored, and controlled. From a basic flashlight to that supercomputer in your pocket, every electrical product is really just a network of interconnected components. These are the small, standardized parts that every circuit is built from. And honestly, learning what each part does, its symbol, and its rating is absolutely the first step to reading or designing any schematic. So what exactly is an electrical component anyway? By definition, it's a discrete device with two or more terminals that performs a specific, predictable function when you plug it into a circuit. Let's actually break that down for a second, because 4 key things define it. First, it has 2 or more terminals. These are the conducting leads that wire it into the rest of the circuit. Second, it has one very clear function, like limiting, storing, amplifying, switching, or supplying power. Third, it operates within rated values. That means there are fixed, safe limits for voltage, current, and power that you absolutely cannot exceed. And finally, every single component has a standard, globally agreed upon symbol, so any engineer, anywhere on the planet, can read the exact same schematic. Think of this as your ultimate visual cheat sheet. We are basically bridging the gap between the messy real world and the abstract language of engineering. For every standard component out there, there's the physical part you hold in your hand, a cutaway diagram of its internal structure, and the standard symbol you'll draw or read on a schematic. It's kind of like the Rosetta Stone for electrical engineering.
Moving right along to Section 2, Passive and Active Families, classifying by energy.
The real dividing line here is all about energy. Passive components? Well, they cannot supply net energy to a circuit. They can only store, release, or dissipate the energy that's handed to them, and they definitely cannot amplify a signal. You don't need any external power supply to make them work. We're talking resistors, capacitors, inductors, transformers. A passive part can literally never give out more than it took in. Active components, on the other hand, can deliver energy into a circuit or actively control the power flowing through it. They provide gain, switching, rectification, and they normally need an external DC supply to do their job. Think batteries, transistors, integrated circuits. Quick side note though, a few textbooks actually group the diode with passive devices since it can't deliver net energy of its own, but it's most often grouped with active parts because of how it controls flow. The big takeaway here: passive parts handle energy, active parts supply, amplify, or control it.
Okay, Section 3. Let's look at the resistor, opposing the flow. A resistor does literally exactly what its name implies. It resists or opposes the flow of electric current. It's got a few core jobs in a circuit. First up, it limits current to protect your delicate, sensitive parts from getting fried by too much power. Second, it can divide voltage in what's known as a potential divider. And third, it takes electrical energy, specifically any extra surplus energy, and turns it into heat, safely dissipating it away from the rest of the circuit.
What's really fascinating here is how the standardized symbol beautifully matches its actual function. If you look at real resistors, like your carbon film, metal film, wire wound, or those tiny surface mount devices, and compare them to the standard zigzag symbol, well, that jagged line perfectly represents opposition to smooth flow. It's exactly like a physical zigzag path slowing down water rushing through a pipe.
And you probably remember the math for this, good old Ohm's law. The formula is V equals I times R. So, voltage equals current multiplied by resistance. It's such a simple yet incredibly powerful relationship. And the standard unit of measurement for this resistance is the ohm, which we represent with the Greek letter omega.
Section 4 already, the capacitor, storing the electric field.
So a capacitor stores energy in the electric field between two conducting plates that are separated by an insulating material which we call a dielectric. The really crucial point is how it behaves in a circuit. It blocks steady direct current, or DC, but it happily allows alternating current, AC, right through. It strongly opposes any sudden change in voltage, and once it's fully charged up, it effectively acts just like an open circuit.
Once again, you gotta love the genius of these electrical symbols. The general symbol for a capacitor is just two parallel lines separated by a gap. It literally mirrors its internal physical structure, two conducting plates separated by an insulator. Simple, right?
The core formula here is Q equals C times V, where Q is the charge. The SI unit of capacitance is the farad. Now, in practical, everyday engineering, you'll mostly see these measured in microfarads, nanofarads, or picofarads, because honestly, a whole farad is massive. Oh, and a highly practical takeaway you definitely want to remember. Electrolytic and tantalum capacitors are polarized. That means the plus lead absolutely matters and has to be connected to the higher potential, or things go bad fast. Now, even though they all do basically the same thing, the stuff inside, the dielectric material, dictates their best use case. Ceramic capacitors are fantastic for general-purpose and high-frequency circuits. Electrolytic capacitors are the go-to for filtering and smoothing in power supplies. Film capacitors, ideal for timing and high-voltage applications. And tantalum capacitors give you incredible stability in a very compact little package.
In reality, these little guys take on a ton of different forms. You've got the colorful, disc-like ceramic ones, cylindrical, electrolytic ones, which usually have a stripe down the side for polarity, and boxy film capacitors. You'll also spot the small, highly stable tantalum ones, and of course the microscopic surface mount or SMD capacitors that literally make ultra-slim modern electronics like your phone possible.
And finally, Section 5, the inductor, which is all about storing the magnetic field.
An inductor is, at its most basic, just a coil of wire. When current flows through that coil, it stores energy in the magnetic field that sets up around it, and any change in that current actually induces an opposing voltage. We describe this behavior using Lenz's law, which basically means the inductor heavily opposes any change in current. Because of this, it passes steady DC with no problem, but strongly resists high-frequency AC. In a steady DC circuit, it essentially just acts as a short circuit.
And this brilliantly illustrates our visual language yet again. Whether it's an air core, an iron core, or a toroidal ring, the standard looped symbol is basically just a literal drawing of the physical wire coil itself. It makes reading a schematic so incredibly intuitive once you know what you're looking at.
The core equation here gets a bit more dynamic. Voltage equals L, which is the inductance, multiplied by the rate of change of the current over time. And because it relies on the magnetic field, its unique unit of measurement is the Henry, represented by a capital H.
Now, I want you to really notice the beautiful inverse mathematical symmetry happening here. Honestly, it might be the most important takeaway of this whole explainer. The capacitor strongly resists a change in voltage, while the inductor strongly resists a change in current. It's like a mirror image, and this symmetry forms the very foundation of advanced circuit design.
So, there you have it. We've broken down the fundamental toolkit. Every circuit you use is just an arrangement of these components. The resistor opposes current and dissipates heat. The capacitor stores energy in an electric field. The inductor stores energy in a magnetic field. 3 quantities, 3 units, 3 equations. By mastering this simple vocabulary, just RC and L, you unlock the ability to read almost any practical circuit diagram out there. The entire language of modern technology is literally at your fingertips. So, with this knowledge in your toolkit, what amazing circuits will you be able to read and design next? Thanks so much for joining me for this explainer.